Mercury should be the easiest planet to reach. It is the closest world to the Sun, a small gray sphere circling just beyond the glare. On the diagrams we saw as children, Mercury sits only one step away from Earth, while Uranus and Neptune appear lost in the distant dark. So it seems reasonable to imagine that a spacecraft could reach Mercury quickly, and in one sense, it can. A fast spacecraft can cross Mercury's path in less than half a year. But reaching the planet is not the same as staying there. To enter orbit, slow down, and begin circling that small world, a spacecraft may need the better part of a decade. Bepi Colombo left Earth in 2018. Its destination was not Neptune or Pluto. It was Mercury. Yet its journey was designed to last almost 8 years, carrying it past Earth, Venus, and Mercury again and again before it could arrive at the right speed. Voyager 2, by comparison, crossed the enormous distance from Earth to Neptune in about 12 years. A tiny world in the inner solar system can demand almost as much patience as a journey to the blue edge of the planetary realm. That is the first strange truth of interplanetary travel. Distance does not tell you how long the journey will take. The planets are not quiet islands resting in space. They are moving worlds, each racing around the Sun at a different speed. Mercury completes an orbit in only 88 days. Neptune needs nearly 165 years. Earth moves between them, carrying every spacecraft we launch around the Sun before the interplanetary journey has truly begun. Nothing starts from rest. Nothing waits to be visited. And nothing travels in a straight line. A spacecraft bound for another planet does not point toward a bright dot in the sky and simply accelerate until it arrives. By then, the planet would be somewhere else. Instead, the spacecraft must aim for an empty place where engineers calculate the planet will be months or years in the future. It leaves Earth and enters a new orbit around the Sun. From that moment on, it is not crossing a static map. It is joining a vast celestial clock, trying to meet one moving gear at precisely the right moment. Venus can be reached in only a few months, though its surface can destroy a machine within hours. Mars usually takes around half a year or more, but a human crew that lands there may have to wait another year and a half before the planets allow a journey home. Jupiter can be passed at breathtaking speed, but a spacecraft trying to remain there must surrender much of that speed before the giant planet can capture it. Saturn may require nearly 7 years of travel before the real mission even begins. Beyond Saturn, time changes scale. A child could be born when a spacecraft leaves Earth and become a teenager before that machine reaches Uranus. A mission to Neptune may be designed by one generation, launched by another, and completed by people who were still in school when the journey began. And yet none of these numbers are fixed. A flyby and an orbiter may follow completely different paths. A light probe may travel differently from a heavy lander. A mission launched during one planetary alignment may arrive years earlier than the same mission launched at another time. Even speed can be deceptive. The faster a spacecraft approaches a planet, the more difficult it may be to stop. A machine can win the race across space and still lose the mission because it arrives with too much energy to remain. So the real question is not simply how far away each planet is. The real question is how much motion must be gained, how much must be lost, and how patiently a spacecraft must wait for the solar system to open the right path. Tonight, we will follow that path, from the scorched orbit of Mercury to the quiet blue darkness of Neptune. At each world, we will compare the quickest journey with the journey required to stay. But before that journey can begin, we must leave behind the most misleading picture of the solar system ever created. The planets are not lined up, they are not standing still, and the space between them is not an empty highway. Imagine looking down on the solar system from far above the sun. The planets would not appear as a neat row of colored spheres. They would be scattered around their orbits, moving at different speeds, separated by distances that change every moment. Mercury would race through the inner system. Venus and Earth would follow on wider paths. Mars would move more slowly beyond them. Farther out, Jupiter, Saturn, Uranus, and Neptune would seem almost calm by comparison, though each would still be traveling thousands of miles every hour. Now, place a spacecraft beside Earth. Before its engines ignite, that spacecraft is already moving around the Sun at nearly 67,000 miles per hour, because Earth is carrying it along. This inherited motion is one of the most important facts in spaceflight. A rocket does not begin its interplanetary journey from a motionless platform in an empty universe. It begins on a planet that is spinning, orbiting, and falling continuously around the Sun. When the spacecraft leaves Earth, it keeps much of Earth's orbital velocity. From there, the engines do not simply push it toward another planet. They change the shape of its orbit around the Sun. To travel outward toward Mars, Jupiter, or Neptune, the spacecraft must gain orbital energy. A carefully timed engine burn raises one side of its solar orbit, stretching it farther from the Sun. To travel inward toward Venus or Mercury, the spacecraft must do the opposite. It must reduce its orbital energy, allowing its path to fall closer to the Sun. This may sound backwards. You might imagine that reaching an inner planet means simply letting the Sun pull the spacecraft inward, and the Sun will pull it inward. But as the spacecraft falls, it accelerates. By the time it reaches the inner solar system, it may be moving far too quickly to enter orbit around a small planet like Mercury. Falling inward is easy. Arriving slowly is not. For most interplanetary missions, the path resembles part of a long ellipse. Earth lies near one end of that ellipse, and the destination lies near the other. This is often called a transfer orbit. The spacecraft performs a major engine burn near Earth, enters the new orbit, and then spends most of the journey coasting. Its engines may remain silent for weeks or months. The spacecraft is not being driven across space like a car along a road. It is following a curve created by its velocity and the gravity of the Sun. In a very real sense, it is falling around the Sun. The destination planet must arrive at the intersection point at exactly the same time. If the spacecraft arrives too early, the planet has not reached the meeting place. If it arrives too late, the planet has already passed. There is nowhere to stop and wait. A spacecraft cannot pull over beside an orbit and remain parked while a planet circles back. It would continue moving along its own path, perhaps missing the target by millions of miles. This is why every mission begins with a launch window. A launch window is a brief period when Earth, the target planet, and the chosen trajectory form the correct geometry. For Mars, a favorable window appears roughly every 26 months. Miss it, and the spacecraft may be ready, the rocket may be ready, and the entire science team may be ready. But the mission still has to wait more than 2 years for the planets to return to useful positions. Venus has its own rhythm. Jupiter has another. For missions that rely on several planetary flybys, the geometry becomes even more delicate. Earth may need to align with Venus, Venus with Earth again, and Jupiter with a destination that the spacecraft will not reach until years later. The mission is planned not only across distance, but across time. This gives every planetary journey at least 3 different clocks. The first is travel time. This is the number most people think about, the months or years between launch and arrival. The second is waiting time. This may include months or years spent on Earth waiting for the launch window to open. The third is mission time. That clock may begin long before launch, during design and construction, and continue after arrival while the spacecraft enters orbit, deploys instruments, and begins its scientific work. A mission described as a 7-month journey to Mars may belong to a project that has already lasted 10 years. A spacecraft that reaches Jupiter after 5 years may have been designed decades before its first close image returns to Earth. And there is one more distinction that changes every number in this story. A spacecraft can pass a planet, or it can stay. A flyby is the faster option. The spacecraft approaches, collects observations, and continues along its path. It may spend only hours near the planet, but it does not need to carry enough fuel to stop. An orbiter faces a more difficult task. It must reach the planet with a velocity that can be reduced by a practical engine burn. If it arrives too quickly, the planet's gravity will bend its path, but it will not hold the spacecraft. The machine will pass through the system and disappear into space. This is why some of the fastest missions are also the least capable of staying. Speed shortens the journey, but it increases the price of arrival. A lander adds another challenge. It must survive the descent, the atmosphere if one exists, the temperature, the pressure, and the surface itself. So when we ask how long it takes to reach a planet, we are really asking several different questions. How long does it take to cross its path? How long does it take to enter orbit? How long does it take to touch the surface? And how long must humanity wait before the solar system offers the opportunity at all? There is no single road to any planet. There are only moving worlds, narrow windows, and carefully shaped arcs around the sun. And nowhere do these rules overturn intuition more completely than at Mercury, the nearest planet to the sun, and one of the slowest destinations to truly reach. Mercury is where the solar system begins to feel impossible. From Earth, it seems almost within reach. It circles the sun closer than any other planet, tracing a small, rapid orbit through the brightest region of the sky. On a simple map, the journey appears to be a short descent inward, past Venus, toward the small gray world glowing beside the sun. But a spacecraft does not see the solar system as a map. It sees it as energy. Earth is already racing around the sun at nearly 67,000 miles per hour. Every spacecraft launched from Earth carries that sideways motion with it. To reach Mercury, the spacecraft must give up a large portion of this orbital energy. That is the real challenge. The spacecraft does not merely need to move closer to the sun. It needs to stop moving around the sun the way Earth does. At first, this sounds as though gravity should help. Reduce the spacecraft's speed slightly, allow it to fall inward, and let the sun pull it toward Mercury. And that is exactly what happens. But the falling spacecraft begins to accelerate. The closer it moves toward the sun, the faster it travels. By the time it reaches Mercury's neighborhood, it may be moving through space at well over 100,000 miles per hour relative to the sun. Mercury is also moving quickly, completing an entire orbit in only 88 Earth days. To remain near the planet, the spacecraft must arrive with a velocity close enough to Mercury's own that the planet's weak gravity can capture it. That is difficult because Mercury is small. Its mass is only a fraction of Earth's, and its gravitational pull is too gentle to seize a spacecraft arriving at extreme speed. If the spacecraft does nothing, it will sweep past Mercury, remain in orbit around the sun, and disappear almost as quickly as it arrived. This is why Mercury has two very different travel times. The first is the time required to encounter the planet. The second is the time required to become part of its world. NASA's Mariner 10 demonstrated the first kind of journey. It launched in November 1973, flew past Venus for a gravity assist, and reached Mercury for its first encounter in March 1974. Less than 5 months after leaving Earth. It became the first spacecraft to visit Mercury and eventually passed the planet 3 times. But Mariner 10 never entered orbit. Each encounter was brief. Mercury appeared, filled the spacecraft's cameras, and then slipped away again as Mariner 10 continued around the sun. A flyby can be fast because the spacecraft does not need to stop. An orbiter must solve the much harder problem of arrival. NASA's Messenger spacecraft launched in August 2004, with the goal of becoming the first machine to orbit Mercury. It did not enter orbit until March 2011. The journey lasted nearly 7 years. During that time, Messenger traveled billions of miles, circled the Sun many times, and performed a carefully planned sequence of encounters. 1 flyby of Earth, 2 of Venus, and 3 of Mercury itself. The spacecraft was not wandering. Each loop removed a little more of the energy it had inherited from Earth. Each flyby reshaped its path around the Sun. Only after years of gradual adjustment was Messenger moving slowly enough relative to Mercury for its engine to complete the capture. This is gravity assist used in reverse. We often imagine a planetary flyby as a slingshot, a way to steal speed from a moving planet and race outward into the solar system. But the same technique can act as a brake. If a spacecraft approaches from the correct direction, the planet's gravity bends its trajectory in a way that reduces its speed relative to the Sun. No physical brake touches the spacecraft. No atmosphere pushes against it. The machine simply exchanges a tiny amount of momentum with a planet, altering its orbit through geometry. At Mercury, one encounter is not enough. The spacecraft must return again and again, each passage trimming away another small piece of unwanted energy. It is less like diving directly toward a destination and more like descending a spiral staircase, circling repeatedly while moving closer to the floor. Bepi Colombo has followed an even more elaborate version of this descent. The joint European and Japanese mission launched in October 2018 carrying 2 scientific orbiters. Its route included 1 flyby of Earth, 2 of Venus, and 6 of Mercury, together with years of gentle thrust from ion engines. Those engines did not produce the violent acceleration of a chemical rocket. They created a faint, continuous push by electrically accelerating xenon ions. The force was small, but it could operate for long periods, slowly reshaping the spacecraft's orbit with extraordinary efficiency. By June 2026, Bepi Colombo had completed the main solar electric propulsion phase of its journey. Its Mercury orbit insertion sequence is scheduled to begin in November 2026, followed by the separation of its 2 orbiters and the gradual lowering of the European orbiter into its science orbit by March 2027. Nearly 8.5 years will have passed since launch. A spacecraft can reach the vicinity of Mercury in months. To arrive gently enough to stay may take most of a decade. And even then, the journey is not over. Near Mercury, sunlight can be more than 10 times as intense as it is near Earth. The planet's surface can become hot enough during the day to melt certain metals, while regions in darkness fall to temperatures hundreds of degrees below freezing. A spacecraft must survive this constant thermal contrast. It must protect its instruments from intense sunlight while still generating power with solar panels that cannot safely face the Sun at every angle. Its radiators must release heat into space even as the nearby planet and the Sun warm the spacecraft from different directions. Mercury has almost no atmosphere to assist with braking. At Venus or Mars, a spacecraft can use atmospheric drag to lose energy. At Mercury, there is only vacuum. Every meaningful reduction in speed must come from engines, gravity assists, or years of careful orbital design. A future lander would face an additional choice. It could descend near the equator, where sunlight and temperature changes are extreme, or target the polar regions, where some permanently shadowed craters may contain water ice. But without a thick atmosphere, there would be no parachute. The lander would need to cancel its velocity with engines all the way to the surface, carrying every pound of propellant required for the descent. Reaching Mercury, orbiting Mercury, and landing on Mercury are therefore 3 entirely different missions. A flyby may take less than half a year. An orbiter may require 6, 7, or 8 years. A lander would require all the patience of an orbiter, followed by a descent that no spacecraft has yet attempted. This tiny planet teaches the first great lesson of our journey. Going inward is not the same as taking a shortcut. The Sun can pull a spacecraft toward Mercury, but it cannot help the spacecraft stop beside it. The closer the machine falls, the more speed it gains. And the more speed it gains, the more carefully it must spend the following years giving that speed away. Mercury's clock is not set by the distance from Earth. It is set by the long, quiet work of slowing down. Beyond Mercury lies another inner world, one that can be reached far more quickly. But there, the journey through space is the easy part. The true challenge begins only after arrival. Venus is often called Earth's sister planet. It is similar in size, similar in mass, and made from many of the same basic materials. From a distance, it appears almost peaceful. A bright world wrapped in smooth white clouds, shining more clearly in our sky than any planet except the Sun and Moon. And compared with Mercury, Venus is surprisingly easy to reach. A spacecraft leaving Earth on a favorable trajectory can arrive in only a few months. The path is shorter. The energy change is more manageable. Venus is large enough to capture a spacecraft more effectively than Mercury, and its thick atmosphere can even help slow an arriving machine. By the standards of interplanetary travel, Venus is close. But closeness is where the kindness ends. A spacecraft approaching Venus sees no mountains, oceans, or continents from space. The entire planet is hidden beneath a global layer of clouds containing droplets of sulfuric acid. Below those clouds, the atmosphere becomes denser and hotter with every mile of descent. At the surface, the temperature is roughly 870 degrees Fahrenheit. That is hot enough to melt lead. The pressure is about 90 times greater than the pressure at sea level on Earth, similar to what a submarine would experience deep beneath the ocean. The air is almost entirely carbon dioxide. There is no breathable atmosphere, no liquid water on the surface, and no cool night offering relief. Because the atmosphere traps heat so efficiently, the nights remain nearly as hot as the days. Venus is one of the quickest planets to reach. It is also one of the most difficult places in the solar system for a machine to survive. The travel time from Earth often falls somewhere between 3 and 5 months, depending on the launch window and the path chosen. That is shorter than a typical journey to Mars. Several early spacecraft reached Venus quickly, and for much of the first age of planetary exploration, the planet became a natural target. It was nearby, bright, and deeply mysterious. But the first missions revealed how hostile that mystery truly was. Some spacecraft failed before arrival. Others lost communication during descent. A few survived long enough to transform our understanding of the planet. The Soviet Venera program achieved what had once seemed impossible. Venera 7 reached the surface in December 1970 and became the first spacecraft to transmit data from the surface of another planet. Its landing was rough. The probe struck the ground harder than expected, and its signal became extremely weak, but it continued transmitting for more than 20 minutes. Those faint signals confirmed that the surface temperature was extraordinarily high. For the first time, a machine built on Earth was speaking from the ground of another world. Later, Venera landers carried stronger pressure vessels, improved thermal protection, and cameras. Venera 9 returned the first images ever taken from the surface of another planet. They showed broken rocks beneath a dim, yellow-orange sky. There were no green valleys, no oceans, and no familiar horizon. Only a scorched landscape under an atmosphere so thick that sunlight reached the ground as a muted glow. Venera 13 survived for more than 2 hours in 1982, longer than any other spacecraft has endured on the surface of Venus. It returned color images, measured the soil, and recorded sounds from the surrounding environment before the heat finally overwhelmed its systems. 2 hours may seem like an extremely short mission. But on Venus, 2 hours is a remarkable victory. The spacecraft did not fail because engineers misunderstood the environment. It failed because no ordinary electronics can remain functional indefinitely inside an oven under crushing pressure. A Venus lander begins dying the moment it arrives. Its insulation absorbs heat. Its internal temperature rises, seals weaken, electronic components drift beyond their operating limits. Every minute of science is purchased with layers of protection that can only delay the inevitable. This creates an unusual contrast between travel time and survival time. A spacecraft may spend 4 months crossing interplanetary space, then only 1 hour collecting data from the surface. The journey can last thousands of times longer than the visit itself. Orbiters have a gentler experience. They remain high above the atmosphere, where the temperature and pressure are manageable. From orbit, radar can penetrate the clouds and map the hidden surface. NASA's Magellan spacecraft reached Venus in 1990 and used radar to reveal vast volcanic plains, mountain ranges, impact craters, and strange circular structures known as coronae. The planet beneath the clouds was not smooth or inactive. It was a world shaped by enormous geological forces. Entering orbit around Venus still requires slowing down, but the planet offers an advantage that Mercury does not: atmosphere. A spacecraft can use a technique called aerobraking, repeatedly skimming through the thin upper layers of the atmosphere. Each pass creates a small amount of drag, gradually lowering and circularizing the orbit without consuming large amounts of fuel. This method must be handled carefully. Too high, and the spacecraft gains almost no benefit. Too low, and atmospheric heating or unexpected drag could damage the vehicle. But when used successfully, the atmosphere becomes a natural brake. It allows a mission to exchange fuel for time. Instead of performing one enormous engine burn, the spacecraft can spend weeks or months making repeated passes, surrendering a little velocity each time. For an atmospheric probe, however, that same air becomes a rapidly changing wall. The probe may enter at thousands of miles per hour. A heat shield absorbs the initial energy. A parachute slows the descent through the clouds. As the probe falls, the pressure rises, the temperature climbs, and the environment becomes less like the sky and more like the deep ocean inside a furnace. The entire descent may last only about an hour. Yet during that hour, instruments can sample the atmosphere layer by layer, searching for noble gases, water vapor, chemical reactions, and clues about how Venus became so different from Earth. This question is one of the reasons the planet remains so important. Venus may once have possessed a milder climate. It may have had shallow oceans or surface water long ago, before a runaway greenhouse effect transformed it. Earth and Venus began with similar sizes and neighboring orbits, yet one became a living ocean world while the other became the hottest planet in the solar system. Reaching Venus is therefore not only a journey to another planet, it is a journey toward one possible fate of an Earth-like world. The numbers appear simple at first. A flyby may take around 3 or 4 months. An orbiter may arrive within several months to a little over a year, depending on its route and braking strategy. A lander can reach the surface on the same general timeline. But the clocks separate after arrival. An orbiter may work for years. An atmospheric probe may survive for about an hour. A surface lander may function for minutes, perhaps hours, before Venus closes around it. Mercury demands patience before arrival. Venus demands endurance after it. One world makes a spacecraft spend years learning to slow down. The other allows a quick approach, then destroys almost everything that comes too close. And beyond Venus waits Mars, the planet that appears easier, safer, and more familiar. It can be reached in months. But for anyone hoping to land, explore, and eventually return home, Mars hides a different kind of delay. The journey there is only the beginning. Mars is the planet that feels closest to becoming real. Its surface has been photographed in extraordinary detail. Rovers have crossed ancient lake beds, Orbiters have mapped valleys, volcanoes, buried ice, and the remains of rivers that vanished billions of years ago. We have watched dust move across its plains. We have heard the sound of Martian wind. And because Mars appears so familiar, it is easy to imagine the journey as something almost routine. Launch from Earth. Travel for several months. Land, explore, then return home. But Mars does not allow such a simple itinerary. A typical robotic mission may reach the planet in roughly 6 to 9 months. Some spacecraft have traveled faster. Others have taken almost a year. Yet those numbers describe only one part of the journey. Mars may be 7 months away when the planets are aligned correctly. At the wrong time, it may be more than 2 years away before the spacecraft even leaves the ground. Earth completes one orbit around the Sun every 365 days. Mars moves more slowly, taking about 687 Earth days to complete its own orbit. As the two planets circle at different speeds, their positions constantly change. Sometimes Earth catches up with Mars, and the two worlds occupy favorable positions on the same side of the Sun. At other times, they are separated by enormous distances, with the Sun lying between them. A spacecraft cannot simply launch whenever its construction is complete. It must wait for Earth and Mars to form the correct angle. For an efficient transfer, Mars needs to be ahead of Earth in its orbit. The spacecraft departs Earth, follows a long elliptical path around the Sun, and arrives months later at the point where Mars has moved to meet it. This opportunity appears approximately once every 26 months. The launch window usually remains open for only a few weeks. If a mission misses that window because of a technical problem, a delayed rocket, or severe weather, it may have to wait more than 2 years for another chance. The spacecraft could be sitting fully assembled. Its instruments could be tested. Its mission team could be ready. But Mars would no longer be in the right place. This is one of the clearest examples of waiting time becoming more important than travel time. A journey of 7 months can be delayed by 26 months before it begins. Even when the launch window opens, there is no single travel time to Mars. NASA's Mariner 4, the first spacecraft to successfully fly past Mars, took about 7.5 months. Mariner 7 followed a faster trajectory and arrived in a little over 4 months. Viking 2 took nearly a year because it carried a heavy lander and followed a path suited to a more complex mission. Perseverance traveled for about 6.5 months before reaching Mars in February 2021. These spacecraft did not disagree about the distance. They followed different journeys because they carried different masses, launched during different alignments, and had different objectives when they arrived. A flyby does not need to stop. An orbiter must slow down enough for Mars to capture it. A lander must enter the atmosphere at a precise angle and survive the descent. A heavy rover demands a different arrival than a lightweight probe. Every additional requirement reshapes the path long before launch. Mars also moves along a slightly elliptical orbit. Its distance from the Sun changes more noticeably than Earth's, which means some close approaches between the two planets are much closer than others. During a particularly favorable alignment, the journey can be shorter. During a less favorable one, the transfer arc becomes longer. This difference may add weeks or months, even though the destination is still Mars. But the most dramatic part of a robotic Mars mission often occurs after the long cruise has almost ended. Mars has an atmosphere, but it is less than 1% as dense as Earth's atmosphere at sea level. That thin air creates an uncomfortable combination. It is thick enough to produce dangerous heat when a spacecraft enters at high speed. Yet it is too thin for a parachute alone to slow a large lander safely to the ground. The spacecraft must use several systems in sequence. A heat shield protects it during entry. A parachute opens while the vehicle is still traveling faster than sound. Retro rockets reduce the remaining speed. Some missions use landing legs, others use airbags. Curiosity and Perseverance were lowered to the surface on cables beneath a rocket-powered descent stage in a maneuver known as the Sky Crane. The entire landing sequence lasts only a few minutes. By the time signals describing the beginning of entry reach Earth, the landing has already happened. Mars can be several light minutes away, so there is no possibility of steering the spacecraft with a joystick. The machine must perform the sequence alone, following instructions written and tested years earlier. For the team on Earth, there is nothing to do but listen. Months of travel end in a short period during which hundreds of events must occur in exactly the correct order. The heat shield must survive. The parachute must open. The radar must identify the ground. The engines must ignite. The spacecraft must recognize hazards and choose a safe landing area. All of this happens before anyone on Earth can know whether the previous steps succeeded. A robotic spacecraft can accept this delay because it has no fear of waiting. For humans, time becomes a much larger part of the mission. A crewed journey to Mars would probably require around 7 to 9 months each way, using a practical, fuel-efficient trajectory. That alone would be longer than most people have ever spent away from the surface of Earth. But the astronauts would not be free to return soon after landing. Earth and Mars must also align correctly for the journey home. When a crew reaches Mars, Earth has continued moving around the Sun. The geometry that allowed the outbound trip is gone. The next efficient return window may not open for roughly 500 days. That's about 16 months spent waiting on or near Mars. The astronauts may complete their primary scientific work in a few weeks or months, but they still cannot leave. The planets have not reached the necessary positions. There is no emergency flight home. There is no faster vehicle waiting nearby. Unless the mission carries an enormous amount of additional fuel for a much less efficient trajectory, the crew must remain until orbital mechanics permits the return. A typical long-stay mission could therefore unfold like this. About 7 to 9 months traveling from Earth to Mars, roughly 500 days living on the surface, then another 7 to 9 months returning to Earth. The full journey approaches 2.5 years. Most of that time is not spent crossing the distance between planets. It is spent waiting for two worlds to move. This waiting period shapes every part of the mission. The crew needs food, water, oxygen, medicine, replacement parts, and dependable power for years. Life support systems cannot merely work most of the time. They must remain functional without regular resupply and without a rescue vehicle close enough to help. Radiation gradually accumulates during the cruise. Microgravity weakens muscles and bones. On Mars, gravity is only about 38% of Earth's, which may reduce some effects, but does not restore the body to normal. Dust could enter equipment and habitats. Communication delays would prevent normal conversation with Earth. Depending on the planet's positions, a message might take several minutes to arrive. A question sent to mission control could require nearly an hour before a full reply is received. The crew would be physically isolated in a way no human group has ever experienced. Antarctic researchers are remote, but help can eventually reach them. Sailors crossing an ocean remain on Earth. Astronauts aboard the International Space Station can return within hours if absolutely necessary. A crew on Mars would live months away from home, even under the best conditions. And during much of the surface stay, leaving early would not solve the problem. There would be nowhere useful to go. This is why saying that Mars is 7 months away is both true and deeply misleading. 7 months may describe a favorable one-way cruise. It does not describe the launch window. It does not describe the landing. It does not describe the wait for the return path. And it does not describe the total time that people, machines, and institutions must remain committed to the mission. Mars has another clock as well. The clock of preparation. A crewed mission would require cargo flights before the astronauts depart. Habitats, power systems, supplies, and perhaps equipment for producing oxygen and fuel from Martian resources might need to be sent ahead. Some of these systems would have to land and prove that they were working before a crew was allowed to leave Earth. The human journey might therefore begin with robotic missions launched years earlier. By the time the astronauts finally step onto Mars, the full exploration campaign may already have been underway for a decade. Mars is often described as humanity's next destination. But it is not simply a place waiting at the end of a 7-month flight. It is a moving world that opens its door only at certain times. It allows arrival, then quietly closes the path home. For a robot, Mars may be a journey measured in months. For a human being, it is a commitment measured in years. And even Mars is still part of the relatively compact inner solar system. Beyond it lies Jupiter, where the distances grow. The gravitational forces become enormous, and a spacecraft faces a new contradiction. It can arrive quickly, or it can remain. Doing both is far more difficult. Beyond Mars, the solar system opens into a much larger emptiness. The rocky planets fall behind. The sunlight begins to weaken. The distance between worlds grows from tens of millions of miles to hundreds of millions. And waiting beyond the asteroid belt is Jupiter. It is not simply another planet. Jupiter is a gravitational kingdom. More than twice as massive as all the other planets combined, it dominates the outer solar system. Its magnetic field stretches millions of miles into space. Its gravity controls dozens of moons, shapes the asteroid belt, and redirects comets that wander too close. For a spacecraft, Jupiter can be either a destination or a doorway. It can pull a machine inward, bend its trajectory, and throw it towards Saturn, Uranus, Neptune, or even beyond the solar system. But the same gravity that makes Jupiter useful also makes it difficult to stay. A spacecraft can reach Jupiter surprisingly quickly if it has no intention of stopping. New Horizons demonstrated this in 2007. Launched on its journey to Pluto, the spacecraft reached Jupiter only about 13 months after leaving Earth. That was remarkably fast for a world orbiting more than 5 times farther from the Sun than Earth does. But New Horizons was not trying to enter orbit. It approached Jupiter at enormous speed, observed the planet and several of its moons, then used Jupiter's gravity as a giant slingshot toward Pluto. The encounter gave New Horizons thousands of additional miles per hour. It crossed the Jovian system like an arrow passing through a storm. For a brief time, Jupiter filled its instruments. Then the planet began shrinking behind it. New Horizons could travel quickly because it did not need to remain. At the speed it was moving, slowing into orbit would have required an amount of propellant far greater than the spacecraft could carry. This is the central contradiction of Jupiter. The faster you arrive, the harder it becomes to stay. A flyby mission can accept almost any arrival speed. The spacecraft gathers what data it can during the encounter and continues into space. An orbiter must do something far more delicate. It must arrive with a manageable velocity, then perform a precise engine burn to reduce that velocity enough for Jupiter's gravity to capture it. Too little braking, and the spacecraft escapes. Too much braking, and it may fall into an orbit that carries it dangerously close to the planet or into its intense radiation belts. The journey must be designed years in advance so that one brief maneuver occurs at exactly the right place, at exactly the right speed. This is why orbiters usually take much longer than flyby missions. Galileo became the first spacecraft to orbit Jupiter, but it needed more than 6 years to reach the planet. Its route was not direct. After launch, Galileo traveled inward toward Venus, returned past Earth, circled the Sun again, and flew past Earth a second time. Each planetary encounter changed its speed and stretched its orbit farther outward. To an observer watching from above the solar system, the spacecraft would have seemed to loop around the inner planets before finally escaping toward Jupiter. The path added years. But without those gravity assists, Galileo's launch vehicle could not have given the heavy spacecraft enough energy to reach Jupiter. The long route was not a mistake. It was the only practical road available. Gravity assists are often described as free acceleration, but they are really exchanges of motion. A planet is already moving around the sun. When a spacecraft passes behind it, the planet's gravity pulls the spacecraft forward, bending its path and adding speed relative to the sun. The spacecraft carries away a tiny amount of the planet's orbital momentum. The planet slows by an immeasurably small amount. The spacecraft may gain thousands of miles per hour. It is like a small boat being pulled briefly into the wake of an enormous moving ship. The ship barely notices. The boat leaves moving much faster than before. Jupiter is especially useful because it is so massive. A close flyby can transform a spacecraft's path through the solar system. Pioneer 11 used Jupiter to reach Saturn. Both Voyager spacecraft used Jupiter to continue outward. New Horizons used Jupiter to shorten its journey to Pluto by several years. Without Jupiter, many of the most famous missions to the outer solar system would have been slower, more expensive, or impossible with the rockets available at the time. But an orbiter cannot simply borrow speed forever. Eventually, it must give some of that speed back. When Galileo approached Jupiter in December 1995, the spacecraft faced the most important engine burn of its journey. For nearly 6 years, it had crossed interplanetary space. It had survived repeated changes in temperature, constant radiation, and the failure of its main communications antenna to fully open. Engineers had spent years finding ways to rescue the mission, compressing data and rewriting software so Galileo could still send useful information through a much weaker antenna. Then, after all that time, the spacecraft reached Jupiter. The arrival burn lasted less than an hour. Galileo fired its engine while passing close to the planet, slowing just enough to become gravitationally bound. Years of travel were decided by minutes of engine operation. If the burn had failed, Galileo would have passed Jupiter and continued into the dark. There would have been no second attempt. The spacecraft became the first artificial satellite of Jupiter and spent almost 8 years exploring the system. It studied volcanic eruptions on Io. It found powerful evidence that Europa hides a global ocean beneath its frozen surface. It observed Ganymede, the largest moon in the solar system, and discovered that it possesses its own magnetic field. The long journey created the opportunity for years of discovery. But Galileo also revealed another hidden cost of traveling slowly. Every additional year in space is another year in which something can fail. Moving parts can stick. Electronics can degrade. Radiation can damage components. Tiny impacts can weaken surfaces. Power systems gradually decline. A longer trajectory may reduce the fuel required at arrival, but it increases the length of time the spacecraft must remain healthy before its main mission even begins. Juno followed a somewhat shorter path. It launched in 2011, traveled beyond Earth's orbit, then returned for a gravity assist at Earth 2 years later. That encounter increased its speed and redirected it toward Jupiter. Juno arrived in 2016, almost 5 years after launch. Once again, the spacecraft had to slow down. Its engine burned for roughly 35 minutes, reducing its speed enough for Jupiter to capture it into a long, looping polar orbit. Juno does not circle close to the planet continuously. Instead, it spends much of each orbit far from Jupiter, then dives rapidly over the cloud tops before moving outward again. This unusual path limits the time the spacecraft spends inside the most dangerous regions of Jupiter's radiation environment. Radiation is one of the great challenges of the Jovian system. Jupiter's magnetic field traps high-energy particles and accelerates them to extreme velocities. Near the planet, these particles can damage electronics, interfere with instruments, and slowly destroy unprotected spacecraft systems. Juno carries many of its sensitive components inside a thick titanium vault. Even with this protection, every close passage exposes the spacecraft to an invisible storm. A mission to Jupiter is therefore not only a question of how long it takes to arrive, it is also a question of how long the spacecraft can survive once it gets there. The moons present their own challenges. Europa is one of the most fascinating worlds in the solar system, but it lies deep within Jupiter's radiation belts. A spacecraft remaining continuously near Europa would receive an enormous dose of radiation. A safer strategy is to orbit Jupiter and make repeated close flybys of the Moon, approaching for brief periods before retreating into less dangerous space. This creates another kind of mission clock. The spacecraft may reach Jupiter after 5 or 6 years, yet require several more years of carefully timed encounters to complete its study of a single moon. Jupiter's vast system cannot be understood in one pass. Its clouds change. Its storms evolve. Its moons move through magnetic fields and cast shadows across one another. To truly study Jupiter, a spacecraft must remain, return, compare, and wait. That depth of knowledge always costs time. A fast flyby may reach the planet in little more than a year. A practical orbiter often needs around 5 or 6 years. A complex mission focused on the icy moons may spend even longer in transit, then require years of repeated encounters after arrival. All these journeys lead to the same planet. Their timelines differ because their intentions differ. The quickest spacecraft is the one willing to leave. The slower spacecraft carries the tools, fuel, and patience required to become part of the Jovian system. And once Jupiter has been reached, the planet can offer one final gift. Its gravity can throw a spacecraft farther into the darkness, toward the pale rings of Saturn. But even with Jupiter's help, reaching Saturn and remaining there requires a journey measured not in months, but in a substantial portion of a human decade. Saturn is often the planet people recognize before they know anything else about it. Even a small image is enough. A pale golden world, encircled by rings so wide and delicate that they seem almost unreal. From Earth, Saturn appears calm, distant, perfectly balanced. But reaching that quiet world is not a simple continuation of the journey to Jupiter. Saturn orbits nearly twice as far from the Sun as Jupiter does. The sunlight is weaker, the communication delay is longer, and a spacecraft that intends to stay must arrive with enough fuel, precision, and patience to surrender years of accumulated speed. The fastest visits to Saturn have been flybys. Voyager 1 reached the planet a little more than 3 years after leaving Earth. Voyager 2 arrived in about 4 years. Both spacecraft used Jupiter's gravity to reshape their paths and accelerate them toward Saturn. They approached quickly, collected images and measurements, then continued onward. Voyager 1 passed close to Titan, Saturn's largest moon. That encounter was scientifically valuable, but Titan's gravity bent the spacecraft sharply away from the plane of the planets, ending any possibility of visiting Uranus or Neptune. Voyager 2 followed a different path. Its Saturn encounter preserved the route toward the ice giants. These missions moved quickly because they did not need to remain. They photographed Saturn's rings, measured its atmosphere, and revealed an intricate family of moons. Then Saturn released them. An orbiter must ask the planet for something more difficult. It must not merely pass through the system. It must become part of it. Cassini was built for that deeper kind of journey. The spacecraft launched from Earth in October 1997, carrying instruments for studying Saturn, its rings, its magnetic environment, and its moons. Attached to it was the European Huygens probe, designed to descend through the atmosphere of Titan. Together, Cassini and Huygens formed one of the most ambitious planetary missions ever attempted. But the rocket that launched Cassini could not place such a heavy spacecraft on a direct, high-speed path to Saturn. The mission needed help from the planets themselves. Cassini first traveled inward. It flew past Venus in April 1998. Then it returned for another Venus flyby in June 1999. 2 months later, it swept past Earth. December 2000, it encountered Jupiter. Each flyby altered the spacecraft's orbit around the Sun. Venus and Earth gradually increased its energy. Jupiter provided the final major push toward Saturn. The route may look strange on a map. A spacecraft intended for the outer solar system first moved closer to the Sun, then crossed Earth's orbit again, before finally traveling outward. But in orbital mechanics, the shortest-looking path is not always the most practical one. Cassini followed the path that allowed a spacecraft weighing several tons to reach Saturn, while still carrying enough fuel to enter orbit. That gravitational choreography took years. After the Jupiter flyby, Cassini entered a long coast. Saturn remained ahead in the darkness, too distant to appear as anything more than a bright point. The spacecraft traveled silently for more than 3 additional years. Its instruments were checked. Its trajectory was adjusted. Its systems endured the cold, and all the while, Saturn grew slowly larger. By the time Cassini arrived in July 2004, nearly 6 years and 9 months had passed since launch. For many missions, arrival means the end of the journey. For Cassini, arrival was the most dangerous moment of all. The spacecraft approached Saturn too quickly to remain. Without intervention, the planet's gravity would curve Cassini's path and send it back into interplanetary space. To be captured, the spacecraft needed to reduce its speed relative to Saturn by more than 1,300 miles per hour. The main engine had to perform a continuous burn lasting approximately 96 minutes. That engine had spent years traveling through vacuum. It had no opportunity for repair. There was no nearby spacecraft to assist. And because Saturn was so far from Earth, mission controllers could not guide the maneuver in real time. At that distance, a radio signal required more than an hour to cross the space between Saturn and Earth. By the time engineers received confirmation that the burn had begun, the critical event was already deep into its sequence. Cassini had to act alone. Before the maneuver, the spacecraft turned its large communications antenna forward to serve as a shield against ring particles. It then passed through a gap between 2 of Saturn's faint outer rings. The region had been chosen carefully, but no path through the rings could be considered entirely free of risk. Even a small particle striking at interplanetary speed could damage the spacecraft. Then the engine ignited. For 96 minutes, Cassini slowed. Saturn's gravity pulled on it. The spacecraft crossed the ring plane, entered the planet's immense magnetic environment, and continued burning fuel until its path changed from an escape trajectory into an orbit. When the engine shut down, Cassini belonged to Saturn. The journey from Earth was over. The mission could finally begin. That distinction is easy to overlook. Cassini spent almost 7 years reaching the starting line. It then spent 13 more years studying Saturn. During that time, the spacecraft changed our understanding of the entire system. It watched storms form and spread through Saturn's atmosphere. It examined the rings at resolutions never seen before, revealing waves, gaps, clumps, and structures shaped by the gravity of small moons. It discovered lakes, and seas of liquid methane on Titan. It found that Enceladus, a small icy moon once thought to be inactive, releases enormous plumes of water vapor and ice particles from fractures near its south pole. Those plumes contain salts, organic compounds, and evidence of chemical activity beneath the surface. Cassini revealed that Enceladus hides a global ocean beneath its frozen crust. A world that had appeared small and unremarkable became one of the most promising places to search for habitable conditions beyond Earth. None of this could have been discovered during a single fast flyby. The rings change with time. Storms evolve. Moons move through different positions. Plumes vary. To understand a planetary system, a spacecraft must observe it repeatedly. It must wait for seasons, eclipses, alignments, and changing illumination. Cassini's long residence allowed scientists to compare Saturn with itself across more than a decade. The Huygens probe added a journey within the journey. In December 2004, the probe separated from Cassini and coasted alone toward Titan. Several weeks later, it entered the Moon's thick atmosphere. Huygens descended beneath a parachute for more than 2 hours, measuring winds, clouds, temperature, and atmospheric chemistry. It emerged beneath the haze and photographed channels that appeared to have been carved by flowing liquid. Then it landed on a surface scattered with rounded pieces of water ice. Huygens continued transmitting for more than an hour after landing. It remains the most distant landing ever achieved by a human-made object. The probe had traveled nearly 7 years from Earth for a few hours of descent and surface science. Again, the time spent reaching the destination was vastly longer than the close encounter itself. Saturn's timelines depend on what a spacecraft is willing to do. A fast flyby can reach the planet in roughly 3 or 4 years under favorable conditions. An orbiter like Cassini may require nearly 7. A mission designed to explore Titan or Enceladus in detail may spend additional years reshaping its orbit around Saturn before completing its most important observations. The planet is not one destination. It is an entire system. Saturn, its rings, and its many moons form a region so large that even after arriving, a spacecraft may need years to move between the places scientists want to study. And every change of orbit requires fuel, or a carefully planned flyby of a moon. Titan itself can act like a small planetary gravity assist. Cassini repeatedly used Titan's gravity to alter the shape and angle of its orbit, allowing the spacecraft to visit different moons and observe the rings from new perspectives. The same principle that carried Cassini across the solar system continued guiding it after arrival. Gravity remained both the obstacle and the road. Saturn teaches a quieter lesson than Mercury or Jupiter. Mercury shows that a nearby planet can take years to reach. Jupiter shows that speed and stopping work against one another. Saturn shows that arrival may only be the beginning. The 6 years and 9 months Cassini spent in transit were not the mission's full story. They were the long prelude before the first chapter. And beyond Saturn, the scale changes once again. The next planet lies so far away that a spacecraft can spend most of a childhood traveling toward it. Only one machine has ever seen Uranus up close. Its visit lasted hours. The journey took more than 8 years. Beyond Saturn, the solar system becomes quieter. The sun is no longer a brilliant presence dominating the sky. It has faded into an intensely bright star, still powerful enough to illuminate the planets, but too distant to provide the warmth we associate with daylight. The spaces between worlds grow enormous. A spacecraft leaving Saturn for Uranus does not pass through a busy region filled with obvious landmarks. It enters years of darkness, following a path through a part of the solar system that humanity has barely explored. Only one spacecraft has ever seen Uranus up close. Voyager 2 reached the planet in January 1986, more than 8 years after leaving Earth. 8 years is difficult to feel as a number. A child born on the day the spacecraft launched would have learned to walk, speak, read, and attend school before Voyager reached its destination. During that time, the spacecraft traveled billions of miles, past Jupiter and Saturn, and continued outward into a region no machine had ever visited. There were no photographs waiting to confirm what Uranus would look like at close range. There was no earlier orbiter providing detailed maps. Everything Voyager 2 was about to see would be new. From Earth, Uranus had long appeared as a small, pale disk. It was known to be unusual because the planet rotates almost completely on its side. Its axis is tilted by about 98 degrees, as though some ancient collision had knocked the entire world over. Instead of spinning upright like Earth or Jupiter, Uranus rolls around the Sun. This strange orientation creates seasons unlike anything experienced on our planet. For decades at a time, one pole faces the Sun, while the opposite hemisphere remains in darkness. Then, slowly, the lighting changes as Uranus continues along its 84-year orbit. When Voyager 2 arrived, the planet was near a solstice. One pole was pointed almost directly toward the Sun. The atmosphere appeared calm and nearly featureless in visible light, a smooth blue-green sphere colored by methane gas. At first glance, Uranus seemed less dramatic than Jupiter or Saturn. But beneath that quiet appearance, Voyager found a world full of mysteries. The spacecraft discovered new moons. It examined a system of dark, narrow rings. It measured a magnetic field that was not only sharply tilted, but also displaced from the center of the planet. On Earth, the magnetic field is roughly aligned with the rotational axis. At Uranus, the geometry is far stranger. As the planet turns, its magnetic field sweeps through space in a complex, uneven pattern, creating a magnetosphere unlike any other known world. Voyager also photographed Uranus's major moons. Among them was Miranda. Miranda is small, but its surface is one of the most unusual landscapes in the solar system. The moon appears to have been assembled from different pieces of terrain. There are enormous grooves, ridges, cliffs, and chevron-shaped regions unlike anything seen elsewhere. Some areas appear old and heavily cratered. Others look younger, as though the surface was broken apart and rebuilt by geological forces. Voyager's photographs raised questions that remain unanswered. Was Miranda shattered by a giant impact and then pulled back together by gravity? Did heat from within the moon cause its icy crust to rise, sink, and fracture? Could small moons in the cold outer solar system remain geologically active for longer than scientists once believed? Voyager 2 could not remain to investigate. It approached Uranus at tens of thousands of miles per hour. There was no fuel reserve large enough to slow the spacecraft into orbit. For months, Uranus grew gradually larger. Then the most valuable part of the encounter passed in only a few hours. The spacecraft took images, measured particles and fields, and then continued onward toward Neptune. Uranus began shrinking behind it almost immediately. That brief flyby still represents nearly everything humanity knows from close range about the planet. Telescopes on Earth and in space have continued observing Uranus, revealing storms, clouds, seasonal changes, and details in the ring system. But remote observations cannot replace an orbiter. A telescope can study light reflected from the atmosphere. It cannot directly sample charged particles around the planet. It cannot repeatedly fly close to the moons. It cannot precisely map the gravitational field or watch the magnetic environment change from one rotation to the next. To answer the deepest questions about Uranus, a spacecraft would need to stay, and staying would make the journey much more difficult. Voyager 2 reached Uranus quickly because it used gravity assists at Jupiter and Saturn, and because it did not need to stop. A future orbiter would have to arrive more slowly or carry enough fuel to perform a major braking maneuver. Its route would depend on the positions of Earth, Jupiter, and Uranus at the time of launch. With a favorable gravity assist, the cruise might take around 12 to 15 years. Without the right alignment, it could take longer. These are not fixed travel times. They are estimates built around particular rockets, spacecraft masses, and launch dates. Move the launch by several years, and Jupiter may no longer be in the right place to help. Change the mass of the spacecraft, and the route may have to become slower. Add an atmospheric probe, more radiation protection, or additional fuel, and the entire mission architecture changes. This is why planning an Uranus mission involves more than choosing a destination. Engineers must choose a future version of the solar system. They must predict where each planet will be more than a decade after launch, and design a path through that moving geometry. The spacecraft itself must remain healthy for the entire journey. Its power source must function through years of cold. Its computers must survive radiation and aging. Its fuel lines, valves, antennas, and instruments must operate after spending more than a decade in space. Software may need to be rewritten during the cruise. New generations of engineers may take over from the people who originally built the machine. The team that receives the first close images may not be the same team that watched the launch. This human timeline is one of the hidden challenges of exploring Uranus. A scientist may begin working on an instrument while still early in a career. That instrument could take years to design, test, and assemble. After launch, another 12 or 15 years may pass before the first orbital measurements arrive. By then, the scientist may be approaching retirement. Students who joined the project near the beginning may become senior researchers before the spacecraft reaches its destination. The mission becomes a bridge between different stages of life. It also becomes a test of institutional memory. Knowledge must be preserved across decades. Engineers must document why systems were designed in certain ways. Operations teams must understand software written years earlier. Funding must continue even during the long cruise, when the spacecraft appears to be doing little more than quietly moving through darkness. But the scientific reward could be extraordinary. Uranus and Neptune belong to a class of planets called ice giants. They are different from the rocky worlds, and different from Jupiter and Saturn. Their interiors may contain mixtures of water, ammonia, methane, rock, and hydrogen under pressures so extreme that matter behaves in unfamiliar ways. Scientists still do not fully understand why Uranus releases so little internal heat compared with Neptune. We do not know the exact structure beneath its clouds. We do not know how its tilted magnetic field is generated. We do not know whether its moons conceal oceans beneath their frozen surfaces. Uranus is not merely a distant blue planet. It is an entire category of world that remains largely unexplored, and planets of roughly this size appear to be common around other stars. Understanding Uranus could therefore help us understand thousands of distant planets that telescopes can detect but never visit. A journey there would take longer than a childhood. The science mission might continue for many years after arrival. From the first proposal to the final data, the project could occupy most of a human career. That is the price of staying at Uranus. Voyager 2 paid less time because it accepted only a few hours nearby. It gave humanity a first look, then moved on. Its next destination lay another billion miles farther from the sun. There, the winds move faster than sound. A captured moon releases dark geysers into a nearly airless sky. And a command from Earth requires more than 4 hours simply to arrive. Voyager 2 would need another 3.5 years to reach it. Neptune was waiting at the edge of the planetary solar system. Neptune was the final planet on Voyager 2's long journey. By the time the spacecraft approached it, 12 years had passed since launch. 12 years since Earth had filled its cameras. 12 years since engineers watched the rocket disappear into the sky. During that time, Voyager 2 had crossed the orbits of 4 giant planets, survived intense radiation near Jupiter, passed through the complex system of Saturn, and spent years moving through the cold darkness toward Uranus and then Neptune. The spacecraft had already exceeded the expectations of its original mission. Its instruments were aging. Its power supply was slowly weakening. Its signal had become unimaginably faint. And ahead of it waited a world no machine had ever seen up close. Neptune orbits the Sun at an average distance of roughly 2.8 billion miles. At that distance, sunlight is about 900 times weaker than it is on Earth. The Sun would still be the brightest object in the sky, but it would appear much smaller, illuminating the planet with a pale and distant light. From Earth, Neptune had always looked like a tiny blue point. Astronomers knew its size, its orbit, and some basic features of its atmosphere. But almost everything else remained hidden. Voyager 2 was about to turn that point of light into a world. The journey from Uranus to Neptune took another 3.5 years. There were no major planetary encounters during that time, no rings filling the cameras, no moons passing nearby. The spacecraft simply continued along its carefully calculated arc. Day after day, it moved through a region of space where the distances between meaningful events were measured in years. On Earth, governments changed, technology advanced, children grew older. But Voyager continued toward the same distant target, powered by radioisotope generators and guided by software written in another era. As Neptune approached, communication became one of the greatest challenges. A radio signal from Earth required more than 4 hours to reach the spacecraft. A reply required another 4 hours to return. This meant that every conversation with Voyager 2 involved a delay of more than 8 hours. Mission Control could not respond to events as they happened. If an instrument failed, engineers would learn about it hours later. If a command was incorrect, the spacecraft might execute it long before anyone on Earth knew there was a problem. During the closest encounter, Voyager had to operate almost entirely on its own. The observation sequence was prepared in advance. The spacecraft had to turn at precise moments, point its instruments toward carefully selected targets, collect data, store it, and then rotate its antenna back toward Earth. There was no possibility of real-time correction. The encounter was less like piloting a vehicle and more like sending instructions into the future. Engineers would transmit a command, then wait nearly half a day to discover whether the machine had understood. Voyager's transmitter used only a few dozen watts of power, comparable to a small household light. By the time its signal crossed billions of miles and reached Earth, it was weaker than almost any natural radio noise surrounding the receiving antennas. The Deep Space Network had to listen with enormous dishes positioned around the world. Additional radio telescopes were brought in to help. Every bit of data had to be extracted from a whisper spreading across the solar system. Then, in August 1989, Neptune finally filled the cameras. The planet was not the quiet, frozen sphere many scientists had expected. Its atmosphere was alive with motion. Bright clouds appeared above deep blue bands. A massive storm known as the Great Dark Spot rotated through the southern hemisphere. White clouds formed and vanished near its edges, and the winds were extraordinary. Voyager measured atmospheric speeds exceeding 1,000 miles per hour. They were the fastest winds known anywhere in the solar system. This was difficult to explain. Neptune receives very little energy from the sun. On Earth, much of our weather is powered by sunlight warming the surface and atmosphere. At Neptune, that distant sunlight seems far too weak to drive such violent motion. The answer must lie partly inside the planet. Neptune radiates significantly more energy than it receives from the sun, suggesting that heat remains trapped deep within its interior. That internal energy rises through the atmosphere and helps power its storms. But Voyager could only sample one brief moment in Neptune's long seasons. The planet takes about 165 years to orbit the sun. A storm seen during the flyby might disappear years later. New storms might form. Cloud patterns might shift. To understand the atmosphere fully, a spacecraft would need to remain and watch those changes unfold. Voyager 2 could not. It was moving too quickly. The closest approach to Neptune lasted only hours. The spacecraft passed just a few thousand miles above the cloud tops, closer than it had flown to any of the other giant planets. This low path was chosen partly to redirect Voyager toward Triton, Neptune's largest moon. It was a daring trajectory. A slight navigation error could have reduced the quality of the encounter or placed the spacecraft on a dangerous course. But the calculations worked. Neptune's gravity bent Voyager's path, and the spacecraft swept toward Triton. Triton immediately became one of the strangest worlds ever observed. It is slightly smaller than Earth's moon, but unlike most large moons, it orbits in the direction opposite Neptune's rotation. This retrograde motion suggests that Triton did not form around Neptune. It may once have been an independent object orbiting the Sun before Neptune captured it. That capture would have been violent. Triton's original orbit may have been highly elongated before tidal forces gradually pulled it into the nearly circular path it follows today. From a distance, Triton appeared cold and still. Its surface temperature is among the lowest measured anywhere in the solar system. Nitrogen, methane, and carbon monoxide freeze into solid ice. The atmosphere is extremely thin. And yet Voyager discovered evidence that the moon was active. Dark plumes rose several miles above the surface. They were geysers, carrying nitrogen gas and dark material into the sky before winds spread the particles across long distances. Sunlight may warm translucent nitrogen ice, creating pressure beneath the surface until gas erupts through cracks. Or deeper sources of heat may be involved. Voyager's images were detailed enough to reveal activity, but not detailed enough to explain it. The spacecraft also found a surface that appeared surprisingly young, with relatively few impact craters. This suggested that geological processes had erased or covered older terrain. Triton might even contain a liquid ocean beneath its frozen crust. If so, it would join Europa and Enceladus as another distant world where liquid water may exist in permanent darkness. But Voyager had only one chance to look. It passed Triton and continued onward. There was no orbit insertion, no return flyby, no second season of observation. The most distant close encounter in planetary exploration ended almost as quickly as it began. 12 years of travel led to a few hours near Neptune and Triton. That contrast captures the true scale of the outer solar system. The journey is long because the planets are far apart. The encounter is short because a fast spacecraft cannot easily stop. Voyager 2 reached Neptune in 12 years, only because it used gravity assists at Jupiter, Saturn, and Uranus during a rare alignment of the outer planets. Without that sequence, a low-energy direct route could require decades. An orbiter would face an even harder problem. It would need to arrive slowly enough, or carry enough fuel, to be captured by Neptune. A future mission concept might require roughly 12 to 16 years of cruise time, depending on the launch date, propulsion system, and available gravity assists. The development of the spacecraft could take another decade or more before launch. Then, After arrival, years of orbital adjustments and scientific observations would follow. From the first serious proposal to the final data, a Neptune mission could span 30 or 40 years. A researcher might begin work as a graduate student and receive the most important results near the end of a career. Some people who help design the spacecraft may never see it arrive. That is not because Neptune is impossible to reach. It is because Neptune operates on a timescale that human institutions rarely use. Budgets are planned over years. Political terms are measured in years. Careers change over decades. Neptune asks for all of them at once. It asks a society to begin a project whose reward belongs partly to the future. And the reward would be immense. An orbiter could watch storms form and disappear. It could map Neptune's strange magnetic field. It could study the rings and small moons. It could repeatedly encounter Triton, measuring its gravity, surface composition, atmosphere, and possible internal ocean. It could answer questions that Voyager 2 was only able to reveal. For now, those answers remain more than 4 light hours away. Neptune is not simply the planet at the end of the solar system. It is the world where travel time becomes generational. Voyager 2 showed that humanity could reach it. But the spacecraft also showed the limits of a brief visit. 12 years of silence, a few hours of discovery. Then the planet receding forever into the dark. And with Neptune behind us, we can finally return to the question that began this journey. Could one mission visit every planet? Could a single spacecraft cross the inner worlds, continue past the giants, and complete the greatest planetary tour ever attempted? The answer depends on what we are willing to call a visit. After traveling from Mercury to Neptune, the question seems simple. Could one spacecraft visit them all? Could a single machine leave Earth, pass the inner planets, continue beyond the asteroid belt, cross the realm of the giants, and eventually reach the dark blue orbit of Neptune? In principle, orbital mechanics allows remarkably complex journeys. A spacecraft can gain speed from one planet, lose speed at another, loop around the Sun, return to places it has already passed, and follow paths that look almost impossible on a flat diagram. But there is an important difference between something that is physically possible and something that is practical with the spacecraft we can build today. The inner and outer solar systems demand almost opposite strategies. To reach Mercury, a spacecraft must surrender orbital energy. It must fall inward and gradually slow relative to the rapidly moving planet. To reach Neptune, it must gain energy and climb outward, often using Jupiter and Saturn as gravitational stepping stones. One journey moves down the Sun's gravity well. The other climbs out of it. A single spacecraft could theoretically travel inward first and outward later, but the route would be enormously complicated. It would require carefully timed planetary encounters, years of waiting between them, and propulsion far beyond what most missions can carry. Every maneuver would consume fuel or depend on a planet being in exactly the correct place. Miss one encounter, and the remainder of the journey could become impossible. So the most realistic mission to every planet would not be one spacecraft. It would be a coordinated exploration program. At minimum, 2 spacecraft would make far more sense for a flyby tour. One would travel through the inner solar system. It might visit Venus, Mars, and Mercury in an order determined by the available launch window and gravity assists. The other would travel outward, using Jupiter as the gateway to Saturn and, if the planetary geometry allowed, continuing toward Uranus and Neptune. Even this would not be a simple itinerary. Mars and Mercury do not always align in a way that allows one efficient mission to visit both. Venus might be used more than once, not because scientists need repeated observations, but because its gravity can help reshape the spacecraft's orbit. The outer mission would depend even more heavily on timing. Voyager 2 reached Jupiter, Saturn, Uranus, and Neptune in 12 years. because the four giant planets were arranged in an unusually favorable sequence. That alignment created a path where each planet could redirect the spacecraft toward the next. It occurs only rarely. A spacecraft launched under different conditions might reach Jupiter and Saturn easily, but find Uranus or Neptune far from any useful continuation. The planets do not arrange themselves according to the mission plan. The mission plan must be built around the planets. Under extremely favorable conditions, 2 robotic spacecraft could potentially fly past every planet within roughly 12 to 20 years. That would be the fastest meaningful answer to the title question. But it would also be the shallowest. A flyby provides only a brief window of discovery. The planet grows larger over several weeks or months. The spacecraft collects its best data during a few hours or days. Then the world recedes behind it. There is no second look. No opportunity to return after scientists examine the first images and discover something unexpected. A flyby gives us a portrait. An orbiter gives us a biography. If the goal is to orbit every planet, the mission changes completely. One spacecraft would not be practical. After entering orbit around a planet, it would need enormous energy to escape again. Then it would need additional energy to reach the next planet and slow down once more. Every orbital capture and departure would demand propellant. The fuel required would add mass. That added mass would demand a larger rocket, which would require even more fuel. This cycle is one of the oldest problems in spaceflight. A spacecraft designed to orbit every planet would become impossibly heavy long before it left Earth. The practical solution is a fleet, a dedicated orbiter for Mercury, another for Venus, separate missions for Mars, Jupiter, Saturn, Uranus, and Neptune. Each spacecraft would be designed for the environment waiting at its destination. A Mercury orbiter would need protection from intense sunlight. A Venus mission might use radar to see through the clouds. A Mars spacecraft could carry a lander or rover. A Jupiter orbiter would need radiation shielding. A Saturn mission might focus on Titan or Enceladus. Uranus and Neptune spacecraft would require power systems capable of operating far from the Sun for decades. These missions could be launched separately, but they would not all take the same amount of time. Venus and Mars might begin returning data within a year. Mercury could require most of a decade. Jupiter and Saturn could take 5 to 7 years. Uranus and Neptune would dominate the schedule, each potentially requiring well over a decade of cruise time. If all 7 missions were fully funded, built at the same time, and launched during the earliest suitable windows, humanity might place spacecraft around every planet within a few decades. But space agencies do not normally develop 7 enormous planetary missions at once. Each mission requires engineers, launch vehicles, instruments, operations teams, tracking networks, and years of funding. Resources are limited. Priorities change. Launch dates move. A delay of 1 year on Earth can sometimes add several years to the journey because a gravity assist opportunity has disappeared. A more realistic program would unfold gradually. Some missions would overlap. Others would wait for funding or for the planets to reach useful positions. Under those conditions, orbiting every planet could take 30 to 60 years from the beginning of the first mission to the final arrival. That would not be one project in the usual sense. It would be a multi-generational campaign. The people who approve the first spacecraft might not be present when the last one reaches Neptune. Engineers would hand unfinished work to younger teams. Scientific questions would change while the spacecraft were still traveling. Instruments designed with one purpose might arrive in a solar system that had already revealed new mysteries through telescopes and other missions. And orbiting every planet would still not mean exploring them completely. The rocky worlds invite landers, Mars invites rovers, and perhaps sample return missions. Venus invites atmospheric probes capable of surviving its clouds and pressure. The giant planets have no solid surface, but probes could descend into their atmospheres until heat and pressure destroy them. Their moons would demand separate journeys. Europa, Titan, Enceladus, Triton, and the moons of Uranus are worlds in their own right. A truly comprehensive exploration program would require orbiters, landers, atmospheric probes, rovers, aircraft, and perhaps submarines beneath distant ice. Such a program could continue for a century. And even then, the solar system would not be finished revealing itself. So how long does a mission to every planet actually take? If we only wanted to pass each world, perhaps 12 to 20 years with several carefully designed spacecraft. If we want to orbit every planet and study each one over time, several decades. If we want to explore them deeply, to descend, land, sample, and return, the answer may extend beyond a human lifetime. The true limit is not simply speed, it is ambition. The more deeply we wish to know a world, the longer we must remain beside it. And perhaps that is the final secret hidden inside every travel time. A destination can be reached quickly only when we are willing to leave it almost immediately. To truly understand a planet, we must give it something far more valuable than fuel. We must give it time. From a distance, the solar system can look almost simple. 8 planets circling one star. A sequence of worlds that begins with Mercury and ends with Neptune. But after following the journeys between them, that simplicity disappears. Mercury is close, yet reaching its orbit may require years of careful braking. Venus can be reached quickly, only to destroy a lander within hours. Mars may lie 7 months away, but a human crew could remain committed to the journey for nearly 3 years. Jupiter can be crossed rapidly by a spacecraft that never intends to stop. Saturn may require almost 7 years before the true exploration even begins. Uranus asks for a journey long enough to carry a child toward adolescence. Neptune can demand 12 years of travel for a close encounter measured in hours. Every world keeps a different clock, not because time itself flows differently there, but because each planet moves through a different orbit, at a different speed, within a different region of the sun's gravity. The solar system is not arranged for our convenience. Its paths were established billions of years before the first human looked upward and wondered what might exist among the wandering lights. The planets do not wait for rockets. They do not pause when a mission is delayed. They continue moving, quietly and continuously, whether humanity is ready or not. A spacecraft must learn that rhythm. It must leave Earth during a narrow opening, follow a curved path around the sun, and arrive at a point in space that may be empty when the journey begins. It must trust that a planet will be there months or years later. And if the spacecraft intends to stay, it must arrive not only at the correct place, but with the correct speed. This is why distance alone can never answer the question. The nearest planet may not be the quickest destination. The fastest spacecraft may not be the most useful one. And the longest part of a mission may not be the journey through space, but the waiting for a launch window, waiting for the planets to align, waiting for a signal to cross billions of miles, or waiting for another world to open a path home. Exploring the solar system is therefore not an act of forcing nature to follow our schedule. It is an act of patience. We do not conquer these distances by ignoring the movement of the planets. We cross them by understanding that movement so well that a tiny machine launched from Earth can meet a moving world in the darkness years later. For a few moments, spacecraft and planet travel together. Cameras open. Instruments listen. Data begins its long return across space. Then the mission either settles into orbit or continues onward, carrying the memory of that encounter toward another distant destination. perhaps one day, spacecraft will travel faster. New propulsion systems may shorten the years between worlds. Humans may walk on Mars. Orbiters may circle Uranus and Neptune. Probes may descend through the clouds of every giant planet. But even then, the solar system will keep its own time. The worlds will continue along their ancient paths. Mercury will race through the sunlight. Venus will remain hidden beneath its clouds. Mars will wait for Earth to return to the correct side of the sun. And far beyond them, Uranus and Neptune will move slowly through a darkness so vast that a single season lasts for decades. The planets are not waiting for us. They never were. And perhaps that is what makes reaching them so extraordinary. For one brief moment, across billions of miles and years of silence, a world and a machine built on Earth arrive at the same place. Not because the planet stopped, but because we finally learned how to move with it.